We're going to be looking at the area of a region between two curves today. And to start this off, we're going to be first considering when we have some function f of x, which on a certain interval is always greater than or equal to g of x. So we've got a nice pictorial representation of it here. They're going to be continuous functions, and we're going to be looking at the interval a, b. Now, the area of the region bounded by the two curves and the lines x equals a, that is the first part of the interval we're looking at, and x equals b. So it's the area between f of x, which is this blue curve, we've got g of x, which is red, and these x equals a and x equals b lines. So the area shaded in green here, this one. So to find that, what we can do is we can do a very similar process to what we did when we were just finding the area under a curve. We're going to do, from the interval a to b, we're going to integrate f of x with respect to x, and now we're going to subtract the integral of from a to b of g of x. And due to our nature of integrals, we can put both of these functions inside the same integral there. Now, it doesn't matter if some of the area is above or below the x-axis, because what we could really do is we could translate those two functions up or down, and we would have an equivalent area. So we could translate them, so instead of partially being above and below the x-axis like we have here, we could translate them above it. And if we did that algebraically, so we have f of x, which we have translated up k units, and g of x, where we've done the same. And like we spoke about before, if we put those two integrals together, you can have plus k minus positive k, so plus k minus k, meaning it's equivalent to the original expression. So we don't need to be mindful of areas that are underneath the x-axis when we're looking at the area between two curves here. We're going to be looking at some more interesting situations in a moment, but for now, we're just looking at when we have f of x is always larger than g of x over a particular interval a to b. So let's actually do that for a particular question. So we want to determine the area bounded by y equals x squared minus 4 and y equals the magnitude of x squared minus 4. Now, they haven't given us a particular region that we're working within here, so a quick sketch will help us visualize the situation. X. So if we're looking at x squared minus 4, that's going to be something that looks like this. And if we look at the magnitude of that, well, we're going to have, it looks very much the same because it's always going to be positive, but I'm going to draw this region first. Trying to draw that symmetrically, and then it will go up like this. So if we're looking at the region bound by these two graphs, it's going to be this region in here. So that's why they haven't told us a particular interval that we're working within, because that's already dictated by the two functions. So this goes from -2 and to 2 there. So we're really just interested, in that region that we've shaded here. So, algebraically, we could represent that as going from -2 to 2 of the function that's on top. Now, in that region of interest, the one that's on top is actually this magnitude function. We have the magnitude of x squared minus 4, and we're going to subtract the function that's underneath in that interval, and that's going to be the x squared minus 4. Now, keen eyes among you will notice that I've made a grave error here. That, algebraically, is incorrect. What we need to do is we need to include brackets around that section function, because otherwise that negative sign is not impacting that -4. So, brackets, essential. And to finish it off, dx. Now, we can easily pop that in the CAS. Let's see what it looks like. So I find it useful to use this magnitude symbol. We got the integral here, and there's nice to use the powers. So we should get 64 on 3 units. Let's check that's the case if we did this by hand. So by hand, if we notice something quite nice here, let's look at the symmetry of this situation. This total shaded area, which I've shaded in purple, that is equivalent to the area underneath one of these graphs. So I could just look at the area here, because it's got to have the same size and shape as that curved pink area between that pink graph and the x-axis on that same interval from -2 to 2. Because it's got a magnitude sign, it's kind of tricky. So we could just look at this area and look at making that positive and doubling it. So by hand, we're going to use symmetry. And yes, you're absolutely allowed to use symmetry. It is a very lovely thing to have noticed, and if you just write by symmetry to give evidence for what you're doing, that's appreciated. So we're going to do that equals, we need to make this area that I've now shaded in purple again, we need to make it positive. So let's write that we're going from, instead of -2 to 2, let's do 2 to -2. And remember, we're doubling that area because the area in between that pink graph that I've drawn on the x-axis is equivalent to that blue graph. I know that my drawing skills are not the best, but trust me on that. So that pink graph was easily x squared minus 4 dx. And that's nicely done now. We just have a nice polynomial, so x cubed on 3 minus 4x, which again we're going from 2 to -2 to make it positive. 2, and we're going to have -2 cubed on 3 minus 4 times -2, and that's going to be minus. Now we've got that 2, let's put that bracket, sorry, 2 cubed on 3 minus 4 times 2. Close that bracket, and close that bracket. So that's -16 on 3. And then I've got +8 plus 8. So that's the +8 here, and we've got, that will be negative, but we've got that negative. And putting it all together, -64 on 3. And because it's an area, we need to ensure we include units, so units squared would be appropriate there. Okay, we're going to determine the area in square units between these two curves. Now notice I made a bit of an error when I put this into my CAS. I accidentally included a y equals inside of here. And if we got rid of that, and we just had the function on top minus the function underneath, we would get an appropriate answer. So how do we know which function is on top and which function is underneath? If you have your CAS, you can quickly graph them, and that can show you nicely that we've got that x squared term underneath and that square root of x term on top, but also your knowledge of graphs can be quite useful there. You can use the interactive or action calculate and do the integral through here, but as I've been doing previously in this video, I actually find it more intuitive to just pop in this here. So if we go ahead and pop that in, let's check that we can do this with our calculator. I encourage you to also do it by hand, but I wanted to just reinforce calculator with this question. So we're going to have root x is going to be on top. If you weren't sure, you could substitute in a value. It's the area between the curves, so it would be important to find areas of intersection by letting them equal each other, and we would have 0 and 4 as the two areas here. So we're going to have square root x minus 1 over 8x, and we're not going to put that inside of that square root, we're going to put it outside. And 1 over 8x squared it is, and we're integrating with respect to x, and we said we're going from 0 to 4. Again, set 1 on 8x squared to equal the square root of x, and you'll get these two solutions, 0 and 4. And of course we're talking about real solutions rather than complex solutions. Okay, let's execute that, and we get 8 over 3. So again, you can use this situation here if you find it useful. You can type the expression in and then use the interactive menu. You have your variable, your lower and your upper, but also not required. So we get 8 over 3 as required. Okay, we've got a 2003 exam 1 question here, and you might say, hold on a second, that's a multiple choice question. Aren't they usually on exam 2? Well, in this exam back in the day, written exam 1 was facts, skills and application, so it was multiple choice, and you were allowed to use a graphics calculator, so a little bit different to these days. Let's treat it like an exam 2 question in these days and use our CAS calculator. So we've got the shaded region is bounded by the y-axis, so the y-axis is this wall here, and the curves with the equation y equals x squared minus 1, that's underneath, so that's like our g of x, y equals 2 cos, and then in brackets pi x over 2. So just be careful with these labels, because this is the one that's on top, even though the label is underneath, so that's like our f of x. So we're going to be doing, in this case, we're interested in x going from 0 to 2 of f of x minus g of x dx. So we want to find the exact area of this shaded region. So again, we're going from 0 to 2. So f of x we said was 2 cos pi x on 2. You may hear my washing machine going in the background. I am very sorry. And then brackets x squared minus 1 dx. I reckon one of these answers is one of the distractors if you forget that bracket here. Let's get our CAS and do that. Okay. Oh, whoops. I had the wrong terminal there. Okay, we get 4 over pi plus 2/3, which is equivalent to our answer of E. Now you notice when I got the terminal wrong before, I got a negative answer, and that's going to relate to the fact that these functions are changing which one's on top and which one's on the bottom. We can see that they clearly cross over in this region here. So let's now start to look at that. When curves cross, as I said before, the curve on top and bottom switch, so the area between them becomes negative. So when I accidentally went, instead of being between 0 and 1 like I needed, I went between 0 and 2, I think this area would be going up like that, and then this one would be eventually curling back down again. So it would have a much larger area going on when they swapped which one was on the top and which one was on the bottom, resulting in an overall negative area. So we need to be really careful if we're swapping there. So to determine the area, you need to take the same precautions as when we did signed areas, changing the sign or switching the bounds or the terminals that we have. So you need to examine the situation that you have and look at which one's on top and which one's on the bottom. So here, for example, this is our function f of x, and initially between a and c1 it's on top, but between c1 and c2 we can see it's underneath. So we've swapped it to be g of x on top here. Or you could change the bounds. In the next region, in between c2 and c3, f of x is on top again, so that's going on here. And then between c3 and b, we can see it's underneath. So we've swapped g of x and f of x. So let's look at this first one. We're going to find the area of the region enclosed by the graphs f of x equals x cubed and g of x equals x. So with this, let's draw a quick sketch. Okay. So if we're looking at f of x, which is x cubed, that's going to be something that looks like this. And if we're looking at g of x equals x, let's get our ruler, pop it there, and I might need to adjust my original graph because I don't think it was particularly symmetrical. Let's have another go. That's not bad. Okay, let's label. This was f of x, and that was x cubed, and g of x was x. Okay, so doing this by hand, we would need to break it up into two regions. To know those two regions, we're going to need to know the points of intersection. So the points of intersection, if we're looking at x cubed equals x, let's go to x cubed minus x equals 0. So we can have x squared minus 1 equals 0. So we can have x plus 1, x minus 1 equals 0. So that gives us x equals negative 1, 0, and 1. So that's going to be here, here, and here. Nice and symmetrical. You could use symmetry here, and you could use the fact that this area here is going to be, despite my bad drawing skills, equivalent to this area here. Or you could use the technique that we just spoke about. So let's do both, just out of interest. What disappeared? So first technique. We could go in the region between, this was negative 1 to 0. I can't help but write it as coordinates. 1, 0. There we go. So we could go from negative 1 to 0 for our x values. We had x cubed was on top and minus x. We don't need brackets because it's just x there, dx. And we could add that to, we're going to call that was region A. I don't know. The next region that we have here is region B. So we're going to add that 2 and we're going to change it around. We're going to have from 0 to 1, and now we're going to have x is on top and x cubed is on the bottom. My dog agrees. Or, approach 2, you could use symmetry. You could have 2 lots of one of these, perhaps from 0 to 1, x minus x cubed dx. Regardless of how you do it, you're going to eventually get, let's do this one, minus x to the 4 on 4, 1 to 0, and doing that algebra you should get a half. So really nice. Need to take a little bit of care to notice which function is on top of the other for particular intervals, but it's doable, it really is. Using the CAS, it's a lot more straightforward. So we used a technique like this when we did it by hand. We had to break it up into its various regions. But the CAS is quite elegant. If we just pop a magnitude sign around it and do it for the whole interval, it can work it out. So just use the absolute value function when working with the CAS. Really convenient. Okay, let's look at exam question. This is from 2001. It's exam 1, and we're going to treat this, again, I showed you before, those old exams you're allowed to use a calculator on exam 1 because the format was a little different. So I'm going to use a calculator here. I am going to ask my dog to stop contributing though, one moment. Okay, I've spoken with my dog and she said that she was just reminding me to take care to see which function is above and below and to make sure we use brackets. All very important. She may remind us of that again soon. So we've got 2 curves here. We've got this top curve, well, I shouldn't say top curve because it's on top in one region but not the other. So this one in pink is y equals 2 sine squared x, and then this one in blue, we've got y equals sine 2x. Oh, that's quite nice. We've got these 2 distinct regions here. We have this region here where the blue y equals sine 2x is on top. And we have this region here, that was meant to be green, this region here where 2 sine squared x is on top. So we're going to have to be careful there. The total area of the shaded regions enclosed for the 2 curves in between 0 and pi. Okay, interesting. This one does not require us to actually calculate something. It's more putting together an expression. And immediately we can eliminate some of these possibilities. I notice a and b go from 0 to pi and always has one function minus the other. So at least we've narrowed it down to 3 options. It is important to note though, I believe from 2024 onwards there's only going to be 4 options in multiple choice. So that would be even easier if we had looked at this in that year. So we've gotten rid of 2 options. Now we need to have a little look-see. We see that the region where the functions change which one is on top and which one is underneath is pi on 4. So having a little look here, I can see pi on 4, pi on 4. And this last one's quite interesting. I noticed that this goes from 0 to pi, and it also, within this integral, it doesn't subtract the other function. And we don't have another integral growing from 0 to pi. So it's not like they've broken up that integral into 2 separate ones. One from 0 to pi of 2 sine squared x dx. Minus another integral also going from 0 to pi of the other one, which was y equals sine 2x. So I'm feeling like we've also gotten rid of e as an option here. So let's go ahead and do that. So let's write it as we normally would. We would be going from 0 to pi on 4, and we would have the function on top in that region, sine 2x, minus the function underneath. Don't need brackets because we only have one term there, dx. So let's look at what we've got going on here. So far, D is looking like our best option because I see that's looking right. Let's double check though. In the second region, we would be going, so we're going to add. We're going from pi on 4 now all the way to pi, and we're going to have 2 sine squared x minus sine 2x. And looking at D, that doesn't look like what we had here. Let's check the terminals, going from pi on 4 to pi, but instead they've got sine 2x minus 2 sine squared x. If you noticed, there's a negative sign here. So this question is not just testing your ability to find the area between 2 curves. It is testing your understanding of how to manipulate integrals to get equivalent expressions. So because we've got that negative and we have swapped the order of this, that is equivalent to what we had written above, making D the correct option. So have a practice of those and see how you go.